networks together, essentially fighting against each other. Okay? The generator is going to try to create samples that look realistic enough to fool the discriminator. Okay, so we have one neural network called the generator. We have one neural network called the discriminator. Okay? The generator is going to try to create samples that look real enough to fool the discriminator. The discriminator only has one job. The discriminator has to try to determine whether the sample it sees is real or fake. Okay? So that's how this is going to play. It's kind of it's sort of a game, I guess. If you read the description there, we're talking about the little imp and you. But basically, each one of them has a goal, right? The discriminator wants to be able to tell whether it's seen a fake piece of data or a real piece of data. And the generator would like to be so accurate that the discriminator basically has to guess, right? The discriminator can't really tell, and it essentially has to guess. Okay? So that's where the adversarial part of this comes in. So let me give you a quick example. Okay? Imagine we have this thing called the veal hook. All right? This is not an English word. I believe it's a Dutch word. Okay? But you, as the discriminator, don't even need to know what a veal hook is. You just need to know whether something you see is a veal hook or not. Okay? Because you're going to begin to learn what a veal hook is, because we're going to give you a bunch of images and we're going to say yes it is or no it's not. Okay? So this one is. All right? So we're going to kind of scroll this pretty quickly. This one is not. Again, is this a veal hook from our corpus or from our data set? This is not. All right? Is this one? Yes, this one is. Is this one? No, this one is not. Okay, so this is essentially, we're doing a manual process right here, but this is really what our discriminator is going to be doing. Right? No, it's not, but it's a very good fake. No, it's the same fake as before. No, it's a very creative fake. Okay, so why am I showing you all this? I'm showing you this because we're trying to learn what the essence is of the shapes in our data. Okay? And so we can say that in this case, a veal hook is characterized by three features: color, size, and the number of faces. Okay, so we can represent these images based on three different characteristics. Okay? This set of features or characteristics we often call the latent representation. Okay? And so we're basically reducing something that's fairly complex to just three values, right? Color, size, and the number of faces. Okay, we're going to be doing that in this laboratory. We're going to be using the latent representation in our generator to create new images. Okay? So now if we say that this particular shape is characterized by color, size, and the number of faces, what if we do something like this? Okay? What if we could do something like add and subtract things in our latent space? Again, our latent space only has 3 dimensions, right? Or it's a vector of size 3. So if you kind of look at this equation, you see we have something that's large and red with 3 faces, and something that's small and green with 5 faces. Well, if you add them together, right, you could come up with something that's medium and yellow and 4 faces. Okay? Again, we're reducing the dimensionality of the information. Remember, we gave it images, and now we only have 3 different coordinates to basically characterize our image. Okay, so we're really reducing the dimensionality of the information. You can almost think of it as compression, sort of. Okay, so this is the GAN setup. All right, this is the discriminator and the generator. Now this stuff is really small. I know for you folks in the back, all of these images are going to actually show up in your lab as well. So you don't need to furiously scramble, write this stuff down. You don't need to take pictures or anything like that. But what you can see is our input. So this is the discriminator. This is a neural network. Okay? The input to the discriminator is either real data or it's fake data. Okay, so the discriminator is going to be shown images that are either real or fake. And what it's going to do is it's going to train based on its results of classifying the data as real or fake. Okay, again, the discriminator only has one job. It has to determine whether the image is real or whether it's fake. Okay? And in the training phase, we're actually going to tell it whether it does the right thing or the wrong thing. Right? Ultimately, we want to deploy this thing, and we're not going to be able to know whether the image is real or fake. But in the training phase, we're going to say real or fake. Okay? But this is unsupervised. We haven't said anything about the data set yet. All we've said is there's a bunch of images, right? Now in the upper left, you'll see the generator, okay? Now the really unique thing about the generator, or the cool thing is, it's basically this neural network in reverse, okay? So you see this network, the discriminator, starts out with an input of an image, and you see 3 little square panels here. That's meant to indicate a 3-color channel image, okay? And the output is just one value, 0 or 1, okay? It's real or fake. Now the generator is really just a discriminator in reverse with one small change. Okay, the change is the input. The input is this latent vector, this z vector. Okay, what we think of as being the defining features of these images. Okay, so the input is going to be some random latent vector. It's going to run through this neural network. Again, that's the reverse of that network. And it's going to pop out an image which we hope will fool the discriminator. Okay? And that's where the backpropagation happens here. Basically, it's going to run through here. The discriminator is going to look at it, and it's going to tell us how real or how fake it thinks it is, right? Is it 90% real or is it 10% real? And then this generator will update its weights based on how well it's doing fooling the discriminator. Okay? Again, almost identical networks, just one is running in reverse of the other. Okay? So this is where the N comes from, right? Generative adversarial networks. The network topology, again, is shown up here. This is also in your slide. I know these numbers are very, very small, but these are actually the sizes of the different layers of the neural network. Obviously, with respect to images, you start out with some feature maps and convolutions, and then you end up with some fully connected layers. Okay? So you can read up all about this, and often this is called DC-GAN or DC-GAN, so Deep Convolutional Generative Adversarial Networks. Okay, so our data set, we're going to use 2 different data sets here. The first is going to be the MNIST data set. And even though if you were here this morning, Bill Dally said nobody does anything with the MNIST data set, that may be true in research papers, but for learning, it's a very, very good data set. Because it's small, we can actually run training live, and it's very easy to understand what's going on. Right? So the MNIST data set is a set of handwritten digits, okay? 0 through 9. All right? And so what we're going to do here is we're going to use the MNIST data set to train a generator and a discriminator. Okay? So that means the generator is going to try to do its best to create images of handwritten digits that the discriminator can't tell whether it came from the data set or whether the generator made it. Okay? Now, because we have different classes of digits, in other words, there's only 10 classes of digits, we don't just want any image created, right? We want an image created that actually looks like a real digit. Okay, and what we can do, and this is explained a little bit better in the lab as well, but I just want to point it out real quick, is we can condition the generator and the discriminator to only generate or discriminate one digit at a time. Okay? So that way we can say, okay, create for me all types of 3s. Right? Don't create 4s or 5s or 6s, just create all types of 3s. We can do that with the generator. And then with the discriminator, we can say, okay, we know it's going to be a 3, all right, but is it a real 3 or is it a made up 3? All right? Again, I don't want to belabor this point too much, but you can read through it as we go through the lab. Okay, so that's going to be our first exercise. You're going to have an opportunity to run some training in AWS. If memory serves me, it takes between 5 and 10 minutes. So when you get everything set up, sort of click go, and then you can watch the GPU, or watch the output of the GPU, rather, as it trains these 2 neural networks. And again, the idea is that the discriminator basically is 50% accurate. In other words, it doesn't know whether the image is real or fake. It essentially has to guess, right? And that would be the best case scenario for the generator. Okay, I'm going to skip that. I'm going to skip this, and then talk real quickly about basically an encoder. Okay, so what if we said, okay, I've put all these random z vectors in, these random latent vectors, but what I'd really like to do is I'd like to extract a particular style of an image. I don't just want to put a random z in. In other words, what is Z actually telling me? Okay? And so what we can do is we can figure out, if we change the structure of the two networks slightly, we can figure out what type of style of image actually produces a particular value of Z. Okay? Like maybe we want to do cursive or something like that. Okay? Or maybe we want to write some of the numbers in a more European style versus a more American style or something like that. Okay, so I don't just want to generate any 7. I want to generate 7s that look like they're a particular style. So what you can do, take your data set, run it through the discriminator, okay, but instead of the output being a yes or a no, the output is this Z vector. And again, this Z vector is something you can choose the length of. Right? You can choose it to be 2 or 100 or 1,000 or whatever. In this case, it's 100. Okay? You say, okay, I run this, I get a Z. Now I run it through the generator again, and then I look at the output. In other words, these two networks should essentially be the reverse or the inverse of each other. And if they are, then we're figuring out what Z is. It's a particular style. Okay? So what we're going to learn this way is we're going to actually look at how changes to Z change what types of images are created. Right? We can say, draw a 3, but what style of a 3 do you want? Right? What style of 3? What style of 7? And so that's what the Z vector will help us do. Okay. The second thing we're going to actually do is apply this to celebrity faces. And again, most of what we're going to be doing today is not training, it's inference, because some of these networks take a little bit too long to train in the course of the lab today. But what we're going to do is we're going to work through a series of exercises on celebrity faces using the celebrity faces data set. And essentially what we're going to do is create a face of nobody that exists. But we're going to pick particular things like hair color, male or female, and so forth. Right? Hair length, probably. We can actually do that. And this is actually what you're going to do. You're going to say, okay, is it a man, yes or no, blonde hair, blue eyes, smiling, looking left, pointy nose, and so on and so forth. And you're going to actually generate an image because you know what the characteristics of the Z vector are. Okay? Let's see, let's go another one. Yeah, so this is what we're doing here with the attributes. Okay? So first we started with random Z vectors, but now we're saying, okay, let's actually figure out what the Z vector represents. Okay? So we can characterize these Z vectors, and we can actually say, okay, if I want to extract a particular attribute from all my images, let's say I have 1,000 images, what I actually have to do is take the weighted sum of all the images that have that attribute, let's say black hair, subtract from that the weighted sum of all the images that don't have it, and when I say weighted sum, I mean weighted sum of the Z vector. And what you'll end up with is some new Z vector, and that Z vector exactly characterizes the observation of having black hair. Okay? So if we change the Z vector in such a way, just like this one we just created, we can add or remove attributes from the image. Okay? So if you're not with me fully, 100% right now, don't worry about it, because as we go through the lab, I think it'll make a lot more sense. But it's kind of cool, actually, towards the end when you mess with the celebrity faces, you're actually generating some new face that has never existed, right? You're just basically saying black hair, male, long hair, particular shape of nose, where are the eyes pointed, and so forth. You get to actually create the face this way. Okay? So we're going to be playing with attributes. As an example, if you run this network with a picture with some of these famous people at the top, from top to bottom, Andrew Ng, Jeffrey Hinton, Jan LeCun, and Ian Goodfellow, these are some of the attributes that come out of these images. Okay? So let's see. I don't think we care about that right now or this. So let me get everybody connected now. Again, we're going to get everybody connected, and then you're just going to proceed. And then about halfway through the time, we'll raffle off the Shield TV. And then at the end, we'll probably have a few closing remarks. Okay? But for the most part, it's pretty much self-directed, and all of our TAs will be available for helping you out. So the first thing you're going to want to do, open up your laptop. You're going to want to navigate to this website. okay? nvlabs.quicklab.com. Notice that QuickLab is misspelled, Q-W-I-K-L-A-B. That's on purpose. That's because it's a company, all right? So some of you have accounts and some of you do not. Out of 265 people or so, I think 55 or 60 have accounts. If you do not have an account, go here and create one. You must use the same email address that you used when you registered, okay? Because we have whitelisted all of your email addresses to take this lab today. Okay, so again, nvlabs.quicklab.com. You're not going to get spammed by email or anything like that. We just need a way to verify or authenticate you to take this lab. When you click to agree to the terms of service and choose submit, you'll get a verification email. Okay? So you won't be able to proceed until you get that verification email. All right? Obviously, if you're going through this procedure and you're having trouble, please shoot your hand up and we'll get somebody to help you out. Okay? If you did not register, or if you walked in the door now without having told one of our door people that you showed up, you may not have access, in which case you'll have to raise your hand. We'll grant you access to the lab. Okay? Now, assuming you've all at least navigated to this website, the next thing you'll do is log in. And let me do that real quick so I can show you what this is going to look like. Okay, so very important here, once you get logged in, you're obviously going to want to go to the DLI at Stanford GP University. Okay? None of these other ones, even though they say they're in session, none of them are going to work for us today. Okay? So when you get here, navigate to DLI at Stanford GP University. All right, when you click that, you're going to see the lab called Image Creation using GANs in TensorFlow and digits. You'll click that. Okay? And then up in the upper right corner, it says Start Lab. Okay? So that's where you want to do. Click Start Lab. It's going to take a few minutes for your lab to spin up. Okay? And then once you do that, and once you spin it up, you're going to find something over here that says Launch Lab. You'll click, it's an orange button, you'll click Launch Lab, and it will open up a new browser window for you in a Jupyter Notebook. Okay? If you've never before interacted with a Jupyter Notebook, it's very, very easy. I believe the very top of the lab describes how. If you're on a Windows machine, I think it's Shift-Enter as you go through the cells. But most of this work is done in digits. Okay? So at this point, I'm going to stop, and we're going to make sure people are getting connected okay. And then once you get connected, you can launch the lab. Once you launch the lab, you can just sort of begin powering through it. Okay? And we'll be here to answer questions throughout.
What is the start button?
What is the start button?
Yeah, it's in orange, but I don't see anything.
Yeah, so this is,
Oh, okay.
it's just
Okay. Okay, yeah, all right. Okay, got it. I just said it, the start.
yeah, you did. That
Okay.
did say so.
All right. That's what I'm looking for.
It'll be a screen.
here, image creation. Okay.
You guys ready? How was in the morning?
It was very
every job position has some message be good, right? Yeah, so they asked it less than I expected. No, I had to explain the solution like we did it was not. So I explained. And yesterday I did this what's there, where I use many classifiers, five. Like for example, this is the accuracy. They explained that I did that because I got out data on the CMS labels and app, and I did this now. Naive days was the best one, of course. Even a simple match. It was good because my friend had a department sent me a website how they can do it like this. One day you do about what's good because of this. But I don't know. They might have a guy. That's the problem. Yeah.
Mm.